you so much for the lovely introduction. Let me get my slides up and visible.
Yes, you're ready to go.
Ready. Wonderful. Let me present so we get a full screen. Thank you so much for the introduction, and thank you for having me. I'm really excited to be here. To just add on to the introduction a little bit, at Saturn Cloud, we work on making cluster compute available for data scientists. So if anyone is interested in learning more about that, we have a free trial of our platform that you can use to test out using GPU or CPU clusters to run your machine learning data science code in Python. It's very exciting and really gives you a lot of opportunities to do things that, that you might not otherwise be able to on a local or a single node machine. But today I'm here to talk about actually something quite a bit different, because in a couple of different contexts in my working career, I've had the opportunity to use Airflow and relational databases, including Amazon Redshift, to create data pipelining for modeling and for machine learning workflows. And so I felt like this was really something that I found useful and practical, but also that had a little bit of a challenging entry for new users. And so that's why I wanted to produce this talk and to bring it to you today, so that this sort of option of, which is one of many ways that data processing and data pipelining can be handled, is a little clearer, a little easier for folks to consider and see if it might be the right thing for your business. You can also find the slides that I'm showing and other materials about this at GitHub, and you see the link is at the bottom. And then you can also follow me on Twitter, and I have links to materials like this and other talks of mine there. So when I am bringing this talk to you today, I wanted to make clear that I expect nobody on this in this audience to necessarily know anything about Airflow or Redshift. We're going to cover that. We're going to talk about what they both are, what their functions are in the broader sort of workflow that I'm describing. And we're going to talk a little bit about them really in the data warehousing context, because building a good data pipeline that generates clean, useful data for warehousing is really key to effective scaling of machine learning workflows. If your data is orderly and easy to access for machine learning data scientists or machine learning engineers, then you're really setting up the groundwork for high value machine learning in your workplace. And so then we'll talk a little about what different workflows might be for that. So training as well as prediction or inference and a few other things. And then I'll give you at various points during the talk a little insight into mistakes I've made when I was working in these tools and when I was building out infrastructure with these tools, because there's no reason that you should have to repeat the mistakes that I've already had and solved. So going on, just to give you a quick overview of the things you need to kind of be conscious of and you might be thinking about as you get on with this. Redshift is, and we'll talk about this more in a moment, an AWS tool that is a relational database. The link to installation and getting information about that is right there. It is not free, of course, as I think everyone's probably aware. It does have and we'll talk about this in a moment, a common ancestor with Postgres. So it's actually, if you're thinking about what kind of relational database does this most resemble an open source option, is Postgres. And then we'll talk about Airflow, which is Apache product, and it is open source, so you can see the entire code base, and the installation instructions are at that link. I find that it is really helpful if you're working in an enterprise context and working in these tools to have someone in the DevOps or Ops sort of side of the business to help with some of the scaling and sort of infrastructure needs for this kind of project. But if you don't have a person like that, I still think that you can get a lot out of this and you can still use these tools to be effective. So let's start with Redshift. As I mentioned, it has a common ancestor with Postgres. So if you're familiar with that kind of SQL, of course, SQL is, there are dialects and flavors of various types, but a lot of the syntax and sort of idiosyncrasies that you're familiar with Postgres will be similar in Redshift. It's not entirely the same. You will find odd little quirks that are just for Redshift for a variety of reasons, but it gives you a framework to start from. So one of the really interesting advantages of Redshift that does make for some idiosyncrasies is that they're using columnar storage, which means that the data sort of storage ideology is about data in columns, allowing for really powerful compression algorithms. And I'll have some links at the end of my deck that will tell you a little more about that if you're interested. But this means that there are performance differences that you might have that might not have come across in previous work with relational databases that are more row-based. We'll talk about that a little later. But the Redshift architecture gives you tons of opportunities for parallelization because it's distributed. You can still have clashes, especially when manipulating data, because it is one relational database. But you're really going to see when we look at an architectural diagram of it that the parallelization is a really big advantage. And then, as AWS does with lots of other tools, SageMaker, for example, and other ones, you can programmatically create and destroy instances and clusters in Redshift, so you can really scale up and down resources depending on the size of the data that you're working with, and not have infrastructure that you have spent a lot of resources to create that you don't need. So this is an overview of architecture for Redshift. So this is a distributed data storage solution, as you're seeing, and you may be familiar with other distributed storage options. Elasticsearch is an example of this, but that's of course not relational. And so this diagram shows you at the top client applications, the end user, that's where you might sit. And then your interactions as a user of Redshift will be with the leader node. Queries are sent to the leader node, and the leader is responsible for interpreting a query that's sent, not retrieving the data, but interpreting the best way to divide up the tasks that are contained within that query and pass them to the compute nodes. Those will receive instruction from a leader that's already been interpreted. So it won't look exactly like the query you sent. It will look like sort of a revision of that query to give a chunk of it to the compute node. And then they will run the request for data on slices of data that are split off in each compute node. And so you'll use distribution keys, which we'll talk about a little bit in just a second, to decide how your node slices are going to be divided up. You might use a distribution key that is date-based, so that more data that is on the same timestamp or close timestamps will be sorted together. Or you might use, say, a customer ID, so that customer IDs that are close together will be sorted together, and so on. So there are a few things that are valuable to make sure that you're using Redshift to its full potential. Remember, we're talking about a relational database, so there are keys and interactions between data, but it is distributed. So use that distribution key to make sure that what data you think you'll want to pull together is stored together, and that data that it is organized in a way that makes sense for the relationships within it. You're the only one who can really know that, right? Because this is your business data, and having knowledge about the underlying meaning of the data is key to deciding the right way to store it. One really interesting thing that Redshift allows you to do as well is to ask the database itself for the most appropriate compression algorithms and encodings that it might choose. There are different ways that you can apply compression to different fields in your data. So column-wise, you can set compression choices. And if you run the function analyze compression on the table that you're thinking of creating, or that you've created, pardon me, then it will tell you the appropriate compression, and you can apply that compression after actually creating the table. And that's really nice. In general, when doing work with relational databases, I think that planning strategic concepts are important to think about, because you want to make sure that the data storage you're creating will scale with you, will grow with you, and will adapt to the data that you're going to pass it. We don't always know what's going to change about our data or about our business needs in the future, and that's absolutely understandable. But what we can think about is trying to accommodate expected or reasonable to foresee changes. there's another kind of key that you can use in Redshift in addition to the distribution key, which is the sort key, which will organize your data within the nodes that it's sliced to. And this can be really useful if you choose a sort key that is a field that you often filter by. So if you might be selecting data, you want to store it in the distribution key, that makes sense. That is often a timestamp or something like that. But your sort key might be something different that you use to arrange the data in your queries pretty often. And explain is a nice little function that's on the same lines as the analyze compression function, a helper function to make it easier for you to use this storage effectively. So if you run a query, you're going to send it to your leader node, and the leader node is going to decide how it might interpret that and pass it to the cluster that you're working with. If the leader node receives a query that it determines really the only way to fulfill it is to send all the requests to one cluster and maybe one slice, that's going to be very inefficient because you're not distributing the computational needs at all. It's very expensive on one particular little slice. You can run explain on this function or the query that you're trying to run before you send it to your leader node. And really what it will do is it will produce the process, the plan that it thinks it might use to execute, and it will just give you the plan and say, hey, does this plan look sensible? And if you see that this is going to really be highly cost inefficient, you can revise your query accordingly. So one thing to keep in mind is that Redshift is I find it very eager to help, has a lot of nice functions built in to make your use of it more effective, but it will allow you to do some things that might be imprudent, I guess. So it doesn't require keys. It doesn't require unique keys on fields. You can create tables that have no keys and no relationships embedded that are going to identify its relation to other tables in your database. And that is if you know what you're doing, it can be okay. But if you're building tables that don't relate to any other tables and you're just sort of creating extra content without having a plan for what it is supposed to sort of, how it's supposed to operate, you can be creating sort of technical debt that you're building in tables that only one person understands or only one person knows. And a lot of database systems will sort of have safeguards built in to try and avoid those sorts of situations. And Redshift is not one of them. So that's just one thing I wanted to bring up, that you need to be thinking about the choices you're making and the architecture decisions you're making in your database, because Redshift is not going to force you into the better habits. So here's an example of creating a table in Redshift. If anyone is familiar with using Postgres or using SQL in general, this will all look very familiar. And this is one where I'm using a few different aspects to identify things. So you'll see that this first row is using sort key. So I'm sorting by the customer identifier. And it's also using identity 11 here, which is actually auto incrementing identity key field for this customer, starting at 1 and incrementing at 1, right? So I'm creating an integer that will be unique for every customer I add to this table, and it's going to do that for me. I never have to assign this. I never have to set it again. And that will give me a known unique identifier for customers that I can reuse later on. And I'm setting it as the primary key, even though Redshift is not enforcing a uniqueness on that primary key. So this just gives you a little example there. I also think that there's wisdom in using the copy command, which you can use to copy data from, say, S3 into Redshift, for example, and being more explicit when you use this. This is a very common way to take unstructured, sort of vague data from S3 and put it into your Redshift database so that it's relational and orderly and easy to use for, say, machine learning uses. You don't necessarily need to specify these column names, but I really recommend that you do, because if data comes into S3 with, say, customer home base and customer home base key reversed, you'll never see an error from this copy command unless you've set up the columns and told it what to look for. Just a handy tip that I recommend. So there are a few things that I can tell you not to do with Redshift. One of the things is you might think that the explain function and this stuff about figuring out how to organize your data across your cluster is sort of fluff. It might seem like it's not really that important or not really something to think a lot about. Let me tell you, you're wrong. I have accidentally written a query that was very, very poorly optimized and set it on Friday and came back on Monday and it was still running. Because Redshift will try to do what you ask. It will try very, very hard to complete the request that you've made. But if you've made a dumb request like I did, it will just run and run and run and run and never get there. And so use that explain function, really do the optimization, and you will find a much, much more pleasant user experience. I've already talked a little bit about creating technical debt of excessive tables that are one-time uses. You can use views. You can use those kind of other SQL tools in Redshift to avoid having this sort of thing happen. And so keep your database tidy, and that will make the modeling process and the machine learning tasks at the end a whole lot easier. Optimize, use those keys, use those relationships, even though Redshift isn't going to force you to. And then use the compression, because you really are going to see a tremendous amount of space savings and saving room in your data storage, especially in these days when we're all collecting, as organizations and companies and businesses are collecting data in massive volumes. Really finding an easy, convenient way to reduce the quantity of data storage you're doing can really save a lot of money for your organization. So we've talked a little bit about the data storage option that we're using in this workflow, but I'm going to talk now about Airflow, which is a job scheduling tool for programmatically building, scheduling, and maintaining these tasks that you want to run at some interval. Any interval is usable, even ad hoc. So it's Python based. That's the first thing to keep in mind. So frame your approach to this in thinking of all of the tools that we're going to talk about, and the programmatic sort of syntax we're talking about is Python based. And it uses a thing called a DAG, a directed acyclic graph. And the diagram that I'm showing at the bottom of this slide is exactly what that is. The phrase sounds a little gnarly, but it actually is very easy to sort of work out what it means. Directed means it goes one direction, so it's chronological. It's working in a temporal fashion. Acyclic, it doesn't cycle back on itself. When it gets to the end, there's an end. There has to be one. And then graph is just the fact that it's a diagram of tasks and their relationships to each other. Airflow as a tool allows you to do testing, versioning, and all kinds of monitoring. It has great logging and great UI for visualizing the processes that your tasks are undergoing. And it's open source. You can view the entire code base. It's free. You can make contributions, bug fixes, additions that you think would be valuable. You'll notice that we're talking again about a distributed toolkit, and that I think is, maybe an indication of sort of the way that data science is going in the modern era, because we at Saturn Cloud use distributed tools all the time as well. And so you as the user are on the left side of our screen today, and this part, not the top. And you will be interacting with Airflow through a UI, and that can be connected to your GitHub account, for example. You could create your Airflow tasks and push them to a GitHub repo, and then this workflow will just pull them every 5-10 minutes, however often you decide. But you can view what's going on and how your cluster is operating anytime through the UI. The scheduler and the web server are two tools that then are the intermediary between you and the actual cluster of workers. The web server is serving you the UI. That makes sense. The scheduler is taking all of the requests you make, the jobs that you have tried to put onto the Airflow cluster, and it's deciding where they go, which worker is going to handle each one, and it's deciding how to organize them in the most time and processor efficient way. So I find that this is where your ops guy or lady might be helpful. This is where you might find someone who has a little bit more experience in setting up server-based types of things. Could be someone you want to get in touch with, but it is possible to install this yourself, I promise. And there are great tools and resources online for people to learn more about it. And I've got some links at the end. So the directed acyclic graph is created using what's called a DAG definition file. And so I'm going to talk a little bit about exactly what these are, because it can look a little scary when you're starting out and looking at a DAG definition file and thinking, oh my God, what is all this stuff? So first off, let's just talk about what you're doing in this. You're giving your instructions to Airflow so that it knows what you want to do and how you want it to be done. That's really all it is. So you start off with something about what tools you're going to need to build in. Here's an example. You want to import the Airflow tools, of course, because that's where what you're actually building. You want to import maybe some other Python libraries that you're going to be using here and there. Totally fine. And then you might have custom written tools that are Airflow tools, but you have customized them for your own use cases. We'll talk about that in a minute. And then you might say, if you're working with Redshift, you might have a need to write SQL. That's the way you're going to interact with your database. So you can custom SQL can be written in strings and saved in actually a Python script, and you can import it just like a Python library. So we've given it tools. We know what libraries we need, what modules from Airflow we're going to be working with. We have a good start. But then think about this. We're setting up a job that's going to have multiple tasks doing different little steps, but we need them all to understand that they're part of a single unit. And so what we'll do is we'll create what's called default args and sort of organize that they know who the owner is, when the start of the job is. These are things that are sort of information about the whole package that need to be available to every subtask and everything. So this one includes a couple of things that you'll notice on failure and on success functions. And these are some of those custom functions that I talked about earlier that I have written specifically so that our on-call system, PagerDuty in this case, gets notified when jobs fail or succeed if they've been failed previously. And so we can trigger an alert to the technical person who's on call, or we can resolve it if the job succeeds. So then, now we're into the real meat of the thing. Now we're ready to talk about, okay, what is this DAG all about? We're going to start by just creating sort of the shell of a DAG, this shell of our directed acyclic graph without really any stuff in it yet. So that'll look like this. We have just, okay, start now, create a DAG. We're going to give it a name. Assigning it to an object means that we can reference it again later, of course. And we're going to set the interval of the schedule. You use cron syntax for this, which is maybe not the easiest to understand, but it's certainly very ubiquitous. And then the default args that we set earlier, we're just passing them in here. So it knows everybody that goes inside this DAG, all of our little jobs, they need to have access to these pieces of information. So finally, task time. So we're going to use what are called operators, and we're going to define tasks with these operators. And so let me talk about what an operator is, because this can get a little bit confusing if you're not familiar. A task in Airflow is just setting up an action to happen. You're scheduling, so to speak, that some job should be completed at a certain time. The operator is the class that you call to initialize that action. It's not going to run when you initialize it. We're talking about a class, right? So we're initializing an instance of that operator so that then it's ready to run when our scheduled time arrives. So it's sort of being put in place, ready to go, waiting for the time to come when it will be kicked off. Anything can be an operator. There are operators that are already built into Airflow. The usual easy ones are already built in because people use them a lot, and there's no point in having to rewrite it every time. So a bash script, run one, that's an operator, already exists, don't have to write it yourself. Run a Python script, same thing. So you can write your Python and then just say, Airflow, go to this location, find this Python script, run it when the schedule says so. And that's it. And it really won't take up nearly as much mental energy or extra effort as you might think. For example, take data from S3 and put it in Redshift, run a Redshift command. These are all things that are also built in. So your Airflow operator can really be anything you want. And it's just that class that you call to sell it here's the one we're going to run. Here's where the script is. Just give it a second, get ready, because when the schedule says go, we're going to go. So there's also, of course, ways to write your own custom operators. I find that starting with one that exists already and just tweaking it and then saving it underneath, that's really my preferred way to do it, because I try as much as I can to avoid rewriting things that don't need to be written again from scratch. but you've got lots of options, and there's a whole open source community of people that will be happy to give you advice, input, and help with writing an operator. And you don't need to submit it to the open source project on GitHub. You can just run it in your particular installation of Airflow and have it work for what you need. So now this might look a little scary, but this is how we would actually initialize an instance of this operator class. This particular operator is the AWS Athena operator, which means we're going to run a query on AWS Athena. Athena is the sort of interface tool that you use to run SQL queries on your S3 data storage. That's the basic way of describing it. So in this case, AWS Athena operator is the name of our class, and we are creating a new instance of it called find records. We have told it to give it a name. Naturally, we've told it what DAG it lives in, which is important because remember earlier we instantiated a new DAG instance and gave it the name DAG because we're very creative. We're giving it some query text that is SQL that we've written in a Python script as a string, and we're passing in a built-in Airflow macro. I've put some links at the very end of my deck that talk a little bit more about what these macros are all about. Then we're giving it connection credentials for AWS, which are actually conveniently stored in credentials management in Airflow, so you don't need to handle that yourself. And then we're telling it where to save the results, and that's basically the amount of it. So this is how we would set up the task find records, but remember it's not going to run yet, and it won't run until we tell Airflow to run the job, the DAG that it lives in. So to rehash a little bit, thing that really I think makes this all a lot easier to work with is to understand acyclic graphing, understanding what needs to run and when, and using the parallelization opportunities that exist in that. You can run a lot of stuff in parallel using Airflow if you think about carefully organizing the tasks that need to be run. Use the credentials management. It's so easy because then you can just pass in a keyword for Airflow and it will know exactly what credentials you're using. Can work on that in your GUI. You don't have to use a whole bunch of like environment variables and that kind of thing set manually. And then look at the GUI. That the UX for Airflow is really quite nice, especially for an open source project where there's a lot of sort of slapped together tools out there, which people are doing on their own time. But Airflow has a really great interface for actually figuring out what happened, figuring out where the logs are, seeing how your jobs are running, and figuring out how to optimize. So there are a few things to keep in mind though. When you're working in Airflow, if your worker is holding a lot of data in memory, say you've loaded in a whole CSV or something like that as a pandas data frame, if you don't need all that memory, all of that data to be accessible to the worker at any given time, I recommend not actually keeping that all at once. You can implement streaming things, or you can load certain amounts and not others, and that kind of thing. There's a lot of options, but I have found accidentally that I overloaded workers by putting too much stuff and just loading it in and thinking, oh, this isn't going to be a big deal, and just leaving stuff in memory without actually releasing it. DAG code can be a little complicated, and you can end up with accidentally duplicating things a lot. And this is maybe sort of just general code hygiene, especially in Python. There are opportunities for efficiencies in all of this, and I recommend taking a look at the ways that your DAG code can be a little more streamlined. And then keep track, look at the logs, look at the errors, and make sure that you're keeping track of what manipulations you're doing on your data using an Airflow job, because that will make it easier for you to debug later if something should go wrong. So I'm going to give you a couple of quick practical examples. We're running close to the end of time, so I'll make sure that we get a couple of these in, and then you'll be able to ask me questions after, if on Twitter or online, if you're so inclined. So this is just a sort of overview of the things that we're going to talk a little bit about doing: data warehouse population, scheduling tasks for data analysis and modeling, and then managing and updating your data warehouse including making sure that end users can get a hold of it. Data ingestion workflow might look like this. You start with data in S3 and pass it to Redshift, and really this is a copy command, more or less. However, it includes a lot of really robust error handling and management of retries because you're using Airflow. And Airflow gives you really big advantages in that regard. You can schedule it at the interval that makes sense for you and use really, like, you'll have tools to figure out what went wrong if something should. Updating data, that is a little bit more complicated, because when we're working in this kind of infrastructure, we want to use a single transaction to avoid data loss. So we're going to do a single job of deleting pre-existing data and inserting new data from an intermediate table. And I've got another slide that will explain a little bit more about how that works, but I want to talk a little bit, I want to leave that for you to read, and I want to talk about the machine learning workflows. So here's an example. You can have your training data stored in Redshift. We may have ingested it from S3 using an earlier workflow, for example. And then an Airflow DAG can actually do your model training. And that trained model object can be pickled, stored in S3, or stored wherever is convenient for you. Then your prediction on new data can use the same format of data in Redshift, presumably, pull that trained model object out of S3, and those two sources of data or sources of content can then work together to create new predictions. This whole thing can be run in 2 Airflow jobs as long as your data is stored appropriately in Redshift. And so you can train the model monthly or whatever is appropriate, and then run predictions daily or even more often using Airflow. There's a prediction evaluation workflow. You would just take an additional step of creating a job for evaluating predictions and organizing that with your ground truth data, which you presumably would also store in Redshift, and then output prediction scores to a table. I have the notes here about Update and about the columnar data storage and compression reasons why insert is much easier to work with in Redshift than Update. But unfortunately, I don't think I have time to talk too much about that. But by and large, if you have questions about this, please let me know, and I will be happy to you can find me on Twitter. And that, I think, is it. There's a couple of links here that give you more information, all available on GitHub. But otherwise, I am very grateful that you've had me in, and I look forward to hearing from folks online to talk about these things more.